Hello everyone, welcome! My name is Lara from Theatre of Science and today we are studying the eye. First of all, I want you to just hold your finger in front of your face, bring it towards you and see how far you can bring your finger to your face before your finger gets blurry. In a normal typical eye, it's about 25 centimetres. If you're young, it might be as little as 6 or 7 centimetres. So however good your vision is, your eye is the most incredible structure. We can see incredibly bright things, we can see really dim things, we can see them far, we can see them close. And the eye wasn't invented. The eye developed over 500 million years. That's what you've got in your head. I've got a little puzzle for you. At the end of this session, I'm going to make a model of the eye. This is the unglamorous bit. I've just got a bucket and some sand that I'm going to stick stuff in. What I would like you to tell me is, what 3 things am I not going to use here to make my model eye? So I've got a glass bowl, ice cream biscuit cutter, packet of noodles, apple, torch, hammer, magnifying glass, fishing rod, big black lid from something, and this from a children's toy with a hole in it. Be pondering that. We're just going to play a very quick game. I am going to get you to find a bit of your body in 3 seconds. Find a bit of your body that bends. 3, 2, 1, stop. Did you find it? Yeah, there's loads of bits of your body that bend, aren't there? I mean, nearly every bit of your body bends. Okay, slightly harder. Find a bit of your body that is white. 3, 2, 1, stop. So you could have had your teeth, you had your eyes, tips of your fingernails maybe. Find a bit of your body that is squishy. 3, 2, 1, stop. Yeah. Little known fact about me, very squishy earlobes. Look at the size of those, so squishy. Once you've seen that, you won't ever be able to unsee. And the last one, find a bit of your body that is see-through. 3, 2, 1, stop. What? Did you get that? See, some of you, if you're really on the ball, you might have done something like that, but that's not a bit of your body. The front of your eye, the first thing we get to in the story of this eye is the cornea. It's got to be really tough because it's got to protect the delicate eye behind it. And it's got to be see-through. And it's got to do one other thing, but we'll learn about that with an experiment. 400 BC, Plato and Aristotle are having a debate, okay? Plato says that rays come out of your eye and touch things, and that's how you see them. Aristotle says, no, rays go into your eye, and that's how you see things, okay? So fast forward 600 years, Galen, we'll see him again, so pay attention. Galen, a very, very famous Roman doctor, he draws a lot of diagrams of the eye, he does a lot of animal dissections, he looks at a lot of eyes, he works out a lot of things to do with the eye, and we'll come back to him later. Fast forward another 600 years, and in the Islamic Empire, blindness is the #1 cause of disability. So people in the Islamic Empire are very, very keen to work out how the eye works. A chap called Al-Kindi comes up with some brilliant thinking. Al-Kindi says, well, to me it's obvious. Your ear's got a hole in it. It's hollow. Your ear is designed to let sound in. That's how you hear sound. Now your eye is not hollow, is it? It's full of stuff. And therefore, Al-Kindi says, this is proof that your eye must send rays out. You can tell, look at it, it's not been designed to let things in. Good thinking, Al-Kindi. Another person, Avicenna, says, no. If rays came out of your eyes and that helped you see, someone who wasn't very good at seeing would be able to stand next to someone who was great at seeing, and their rays would help that person see. And that's not what happens. If you're not very good at seeing, you can't just stand next to someone who's got great vision and see better. So Avicenna says, I'm sure that rays must travel into your eyes. Hernane, who drew some beautiful diagrams of the eye, he comes up with something else. Imagine one person looking at an object. Yeah, in that case, I can think maybe, okay, rays come off the object and into that person's eyes, and that's how they see. Maybe even 2 people looking at that object. Yeah, maybe light coming off that object could hit both of them and they could both see it. But Hernane says, you know, what if there were like 3, 4, 5, what if there's 1,000 people all looking at this object, says Hernane. Is it likely that this object is going to give off so many rays that 1,000, 1,000,000 people could all see it and it would look exactly the same to all of them? No, says Hernane, that is highly improbable. Rays must go into your eyes. And then, finally, we get to Al-Hansen, who says So the shadows are doing weird things to my actors, but this is Al Hansen. He was very wise. He says, look, if rays are coming out of your eyes, then eventually whatever stuff was making the rays would empty out, wouldn't it? And then you wouldn't be able to see anymore. And that doesn't happen. And then he says something very wise. The reason you shouldn't believe that rays come out of your eyes is that we have no proof. And you shouldn't believe anything without a good reason. Who was right? Do rays go into your eyes when you see, or do rays come out of your eyes when you see? See, you're probably going to give me the right answer. It's amazing how many of my GCSE students, when they have to draw a ray diagram, still draw a diagram of like a Superman with light coming out of his eyes. Light comes into your eyes, and that is how you see. Light is bouncing off every object. That's how you can see it. Okay, have you got your bowl, got a jug of water, got a coin? As always, if you haven't, I'm going to do it as well so you can watch mine. I'm just using this little bowl, got my coin. I just want you to put the coin to the edge of the bowl. So this bowl's got quite a clear ridge, so you can see, and this is important, I've put it right up against the ridge, haven't I? There you go. Now, I want you to move back or down until you just can't see the coin. It'd be better if someone else did this for you so that you could stay totally still, but if you're good at staying still, pour some water into the bowl and see what happens. So look, the coin is just there. If you're doing it with me, the coin's just there, and now I'm going to pour some water into the bowl whilst trying to stay totally still. What's happened? The coin is back! Oh, maybe the water just moved it. Let's have a look. No, see? It's still right at the edge of the bowl. Let's do that again. The coin's just out of sight. I'm going to pour the water in. Da, 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 da. What is happening? Well, what's happening is, if you've seen my rainbow lesson, which is on YouTube, you might be able to tell me that when light travels through water, it bends. That's right, it bends. Light can't travel through solid objects that aren't see-through. So at the moment, there's loads of light bouncing off that coin in all different directions, but it's not getting into our eyes because this bowl is blocking it. But when you pour the water in, the light that is bouncing off the coin is bent by the water so that it can get to your eyes. When you get to about 16, you'll draw some beautiful ray diagrams to show exactly how that works, but that is enough for now. That is refraction. Well done. So that's your cornea. Get your mirrors. We're going to have a look at the next thing the light hits, which is your pupil. It's the black bit right in the middle of your eye. If you've got a mirror, you could look at your own eye, or you could look at a person in the rooms. Tell me, please, what is that black bit made of? I'll give you 10 seconds to think about it. It's a hole. Did you know that? It's not anything. It's just a hole. And the iris around it, the coloured bit, has muscles in it which contract and stretch to make the pupil bigger or smaller. Now, get your mirror. We're going to have a look at how your pupil works. I want you to keep both eyes really wide open. Cover one of your eyes with your hand, and then have a look in your mirror, and very quickly take your hand away and notice what happens to your pupil. I say it's harder than it looks because as soon as my hand goes over my eye, I end up sort of wanting to squint and shut my eye. Make sure that this eye that you're hiding is really wide open. You should see that you can really notice your pupil really contracting. So the iris, that coloured bit around your eye, is there to make sure the exact right amount of light enters your eye so you get a nice clear picture on the back. The third thing we get to is very, very similar to a magnifying glass, but much more awesome. Your lens focuses light onto the back of your eye, and I'm sure you all know how a magnifying glass works. You have to hold it just the right distance away from the thing that you want to magnify. So if you hold it too far away like that, the thing is blurry. You've got to hold it just the right distance away to make things come into focus. And if you move whatever the thing is you're looking at further away, you've got to move the magnifying glass to keep it in focus. The moon is 240,000 miles away. Now, when you look at the moon, your eyes don't pop 240,000 miles out of your body and into the sky to be able to focus on the moon. So what does your lens do inside your eye that your magnifying glass can't do? It gets thicker and thinner, yet more muscles make your lens thicker and thinner, so it doesn't have to pop out of your face If something's really close to you and you want to bend the light rays a lot, then the lens gets thicker, just like putting more water in the bowl made the light bend more. And if something's really far away, so the light rays don't need bending as much, then the lens gets thinner. I know, it's like magic, isn't it? Right, we're on to one of my favourite little experiments. Once the light is focused beautifully on the back of your eye, which is called the retina, it hits two types of very, very special cells which detect light, and these are the whole reason you can see. They are called rods and cones. I'll tell you about both of them, but while I'm telling you, I want you to do a little job for me. You might have with you yellow and green pens and blue and red pens. Use yellow and green. If you get time, you like drawing, you can do the blue and the red as well. Just want you to draw a simple picture just with the green and the yellow. Make sure that they're all close together. Don't have any white bits in there. I did one in blue and red as an example. You guys get drawing those. I'll give you about 1 minute. I haven't coloured in my little windows. And while you're doing that, I'll tell you all about rods and cones, the two different types of cells that detect light in your eye. Loads more rods in your eye than there are cones. Rods are very good at seeing in near darkness. Your rods can't detect colour, that's why you might have noticed in the night time you can't really see colours. So your rods are very sensitive, but they take quite a long time to work. If you've ever been in bed and someone's turned your lights off, it feels, doesn't it, like suddenly the room is totally pitch black. And then if you wait for a bit, you suddenly realise that you can see the outlines of loads of things in the room and you wonder why you couldn't see them before. And like if you wake up in the night, suddenly you find that you can see loads of stuff. That's because your rods take ages and ages to start working. After 30 minutes in the dark, your rods are 10,000 times more sensitive than they were when the light was first turned off. So if you're scared of the dark, good activity. Lie in bed, get someone to turn the lights off, and just just keep looking around the room and think about the fact that your rods are working slowly. So it'll get less and less dark every minute that goes by. Hopefully you've got drawing some pictures. This activity is to do with your cones. You've got 3 different types of cones in the back of your eye, and they're good at seeing different sorts of colour. Again, if you saw a rainbows lesson, some of them are better at seeing one end of the rainbow, like the reds. Some of them are better at seeing the other end of the rainbow, like the blues, and some of them are better at seeing greens. Find the centre of your picture and just put a little dot. And what we're going to do is stare at the picture without blinking for about 20 seconds. Just stare at the dot. And then take your eyes away and immediately look at a bit of white paper. If you haven't done it, then you can have a look at mine, but look at a white piece of paper in your room. So get staring at your pictures for 20 seconds without blinking. Don't blink at all, just keep staring at the black dot. Keep staring at the black dot. Your eyes might go really weird, but that's okay. And then in a second, you're going to look at a white piece of paper and you're going to see what you can see. I'm not going to tell you what you can see, and we'll see if you can see it. Are you ready? Are you ready? Are you going crazy? Okay, have a look at some white paper. What can you see? Are you seeing the same image, but it's blue and red? Yeah, what you've done is you've tired out the cones that detect yellow and green light. So now you're just looking at something neutral, something white. All your cones are supposed to be working equally, but the yellow and green cones are really tired. So the cones that detect more blue and red light are stronger, so that they're sort of taking over. Did that work for you? If it didn't work, try it afterwards. I've done a red and blue one here as well. I'll hold that up to the camera, or you can draw your own picture. And then if you want to look at that for 20 seconds, then you can. On the YouTube version of this, I'll put a link to something the BBC did where they took a whole massive photo and did that with it, and it's incredible. You look at the photo and then you look at a black and white image and you can see all the colours. It's crazy. Okay, the next thing I want to tell you about, we are going to do by finishing off story time. Do you remember Galen? Very, very famous, well-respected Roman doctor. Well, some things about the eye he got just right. He gave names to the eye that we're still using today. Some of the things about the eye he got very wrong indeed. Galen, no! 1,300 years later, in the 1500s, people were still believing that everything that Galen said was true. Students would go to lectures to learn about the human body, and an assistant would hold up real bits of human body while a teacher read out Galen's description, and if Galen's description didn't match what the assistant was holding up, people would believe Galen's description. That's how powerful he was. That's how much people didn't believe what they saw. They just believed what they already knew to be true, until a very famous scientist called Kepler said that he had discovered the image that you saw was projected through your eye and onto the back of your retina. Now, people didn't like that he said this. They didn't like it because, can you see something weird about what he said? He said that the picture got projected onto your eye upside down. Now, if you have a spoon on you, you can see this for yourself. If you hold up the rounded bit of the spoon, then you will be the right way up. But if you look into the concave bit of the spoon, oh, you're upside down. It's exactly the same with your eye. Like I say, when you're 16, you'll draw some lovely ray diagrams to know how that works properly. It's to do with how the light rays cross as they come into your eye. And we'll do a demo to look at how this is true later, somebody else said that they had discovered a non-seeing bit of the eye. The optic nerve, which Galen had said was hollow, wasn't hollow at all, and then it came off at the side. Now, people didn't like that either, but it didn't mean it wasn't true. And then someone else a few hundred years later said that nerves produced electricity, that our bodies could produce electricity, and someone else proved it 50 years after that. And then someone finally said in the 1900s, it doesn't matter whether you're touching something, hearing something, seeing it, the signal is just sent by an impulse to your brain, and it's the bit of your brain it goes to that matters. So sound waves get turned into impulses which go through your auditory nerve and into one part of your brain, and light and your picture in the back of your eye, it doesn't matter that it's upside down because it gets turned into an impulse and goes through your optic nerve and into your brain, and your brain translates it for you. And literally days ago, scientists announced that they had taken just normal skin cells and managed to turn them into rod cells and put them into the back of the eye of blind mice, and now the mice could detect light. And that was a couple of days ago. We're nowhere near the end of the story. If you want to be a scientist, there is so much cool stuff for you to discover. Let's go back to what that chap said about the non-seeing bit of the eye. You should have a bit of paper with you and a pen. All I want you to do is draw a circle on one side and a cross on the other side. You might want the cross to be a little bit smaller than this one, but about that far apart. Close the eye that is opposite the cross, but with the eye that is open, look at the cross, okay? Close the eye that's opposite the cross, and with your open eye, look at the cross, and move your piece of paper towards your face, and you should see, oh, that happened really fast for me, there should be a point where the circle disappears. And that is your blind spot. That's where this eye can't see. That is why humans are not quite as good as octopuses. You remember I said that the eye wasn't invented, it developed over 500 million years. Nerves carry messages from the cells, the rods and cones in our eye, to our brains. But the nerves are in front of the rods and the cones. And to get to the brain, the nerves have to go through the wall of the eye. Now obviously if there's loads of nerves going through your eye, you can't have any rods and cones there. And that's why your blind spot is there. Octopuses evolved in a different way, and their nerves are on the outside of their eye, so the cells just send a signal to the nerve, and then the nerve goes up to the brain, and they don't have a blind spot. But there you go. It's a nice demo because it tells you a bit about your body you probably didn't know before. And it also shows that loads and loads of what we think of as being seeing with our eyes is actually seeing with our brains. So the reason that the spot disappears is because when it reaches your blind spot, your brain fills in what it thinks is there. And in this experiment, it's just getting it a bit wrong. It's assuming that there's some white paper there. Because the optic nerve comes off at an angle, your blind spots are in different places. So you're not usually aware of your blind spot because you've got two eyes. You can see slightly different things with each eye, and they piece together a whole picture for you. The other reason two eyes is good is because they help with depth perception. So grab two pens for me, any two pens. Close one eye, give them a little wiggle like this, and then try and touch the pens together, and you will find it's very hard to do. Close the other eye, wiggle again, try and touch the two pens together. It's surprisingly difficult. And then do it with both eyes open. You should find that it's much, much easier. Your eyes are in slightly different places, so they're not seeing exactly the same thing. So because your eyes give you slightly different images, you get an idea of depth perception. There's lots of other ways that you can see depth, but that's one of them. Right. That is all I wanted to teach you about the bits of the eye. I'm going to try and show you, I'm hoping it works. It's so cool that if it works, it'll be worth it. We were talking about how your brain is a big part of what you see. don't blink, don't move your eyes, just stare at the middle of the spiral for as long as you can. After 20 seconds, when I say it, just look at your finger. Don't look at what's on the screen so it won't work, but if you look at your finger, you might find that your finger looks like it's getting bigger. Okay, let's have a go. You ready? So stare at the centre of the spiral. I'm doing this with you. Don't blink for 20 seconds. Keep going. Keep going. If you do this at home, it's amazing. Obviously, some of this stuff is a little bit lost with it being on camera. I hope you're not blinking. I hope you're not blinking. I'm really sorry I can't see those comments because I'm just working hard at not blinking and staring at the centre of the spiral. The longer we do it for, the better it will be. And I'm about to pull away and I want you to just look at your finger. See if it looks like your finger's getting bigger, okay? You ready? We can do this after 3. 3, 2, 1. Look at your finger. Wow! Oh, that really worked for me. I hope it's working for you as well. If you want to hang around after this lesson's finished, I'll do it again anti-clockwise and it makes your finger get smaller. There's videos you can watch with spirals on YouTube, but they made me feel really sick, so I couldn't do it. Let's have a look at my model of the eye and see if you guessed correctly. Here's my ugly looking bucket with some sand. The first thing that we need, the glass bowl. You might have guessed that. Can you remember what that's called if it's real in your eye? That is the cornea. The next thing we need is this, which is the iris, the coloured bit of your eye, which contracts to change the size of your pupil, which is the hole. So what we don't need is we don't need this black plastic lid. I thought that might fool you because you might think that there was a black circle in your eye, but there isn't really. I've got a torch with loads of holes and I've sort of tried to turn it into a face. So there should be 2 little dots for eyes and a dot for a smile. So at the moment, not very focused, is it? That's rubbish. Let's put the magnifying glass in there. There we go. You'll obviously need the fishing rods and cones. Yeah, come on. Well done, whoever said you don't need the hammer. You don't need the hammer. The hammer is the name of a bone in your ear. We'll probably look at that later when we do a lesson on music. Is it a packet of noodles or is it a bundle of nerve fibres? Oh, that's going to be our optic nerve. There we go. And you didn't need the apple. There's a phrase, the apple of my eye. That means that it's someone that you love and you're really proud of, but there are no actual apples in your eye. Right, let's see if the... Oh, look at that. Did you see that little face? Can you see that? There's a face peeping out from behind the rod. Let's go. There we go. Look at that. Can you see that? Now, the amazing thing about that, to me anyway, is that if I don't turn this torch around, I don't turn it upside down, I'll show you. Look, the smile's upside down. Can you see the 2 eyes at the bottom and the smile's at the top? But when I put it through my model of the eye, just like in your real eye, it's the right way around. Isn't that cool? And then it's your optic nerve, that bunch of noodles, which sends an impulse to your brain, and your brain sorts it out for you so you don't see the world upside down. And that is the end of our eye lesson, except to say I've done a new thing this week. I have put together a little activity pack. There's 4 different things you can cut out and make and do. Put the stripes onto the zebra. Benham's disc, if you make that properly and spin it, some people can see colours. And what else is there? Oh yeah, there's my favourite optical illusion. My very favourite optical illusion is there. I've put a link to it on my Facebook page. I've made it pay as you feel. So if you pay me anything via PayPal, then you get an email and it's got the activity pack in it, so you can put a penny in and you get the activity pack. As usual, please like my Facebook page and please subscribe to me on YouTube. Bye! If you go to the Minecraft place, they've got a massive eye that you can go inside. Oh, I told you that I would hang around because I'm going to show you that experiment that goes anti-clockwise. Let's do that. Right, I'm going to spin it anti-clockwise now. You ready to stare at the centre? And then look at your finger. Zach says Minecraft is great and you should do it. Alright, what even is it? Is it a computer game? Is it a computer game? Bye, Charlotte. Really had fun my first time. Oh, that's good, Kai. Thanks, Kai. It's all on it's all on YouTube if you want to go back and watch some of the lessons if you've got a few half hours to kill. Thanks, Inara. Nice name. My name's Lara. We rhyme. Roblox. Finn and Callum are amazed by this spiral experiment. Oh, good. Does it work? I wasn't sure. See you next week. Bye.